Now, through this, we've been talking about atomic masses, and we've been using these whole numbers, and really what we've been using are unified atomic mass units. And so when you look at atomic masses of different elements, what that mass is given in is this atomic mass unit. And it's the standard mass unit for atoms and molecules, and you see it a lot, and you've probably used it in chemistry. It's the standard unit for the mass of atoms and molecules, and you used it all last year in chemistry if you took chemistry last year. And the unified atomic mass unit has a specific value in kilograms of 1.6605 times 10 to the negative 27 kilograms. So it's a very, very small mass. And if we are to put it into an energy, it's 931.5 mega electron volts per speed of light squared. And we're going to talk about this unit more in depth here in a minute. But if we were to look at the actual mass of a nucleus, or the actual mass of an atom, we would take that mass, that whole number mass, 100 or 200 or 75 or whatever it happens to be, and we'd multiply it by this 1.6605 times 10 to the negative 27th, and that would give us the mass of the nucleus in kilograms. But as you can see, those are going to be very, very small numbers, and they're generally more difficult to work with, and so that's why the unified atomic mass unit was developed. Now, talking about nuclear chemistry leads us to Einstein's mass-energy equivalence relationship. In 1905, when Einstein was developing his theory of special relativity, he also said that there was this relationship between mass and energy, and that they were essentially equivalent. And this is where the famous equation E equals mc squared comes in. That equation, E equals mc squared, gives the amount of energy that is equivalent to a certain amount of mass. And so we can now say then that all masses have some associated energy that goes along with them. And then this also leads us to the idea that mass can be converted into energy and vice versa. And again, as I mentioned, that energy and mass is related by that E equals mc squared. If we expand it a little bit more, the total energy is equal to mc squared, where m is the mass, c is the speed of light, plus any kinetic energy that that particle might have because of its motion, because it's moving around. And so that gives us then the total energy that any given piece of matter might have. So again, for some particle at rest, our energy within that mass is mc squared. And what this then means is that a unit of energy can be considered a unit of mass. And in a lot of tables for physical constants, you'll see a particle's mass given in kilograms, unified atomic mass units, and mega electron volts. And we'll talk more about mega electron volts when we get into electricity, but the electron volt is a unit of energy that is used for very small amounts of energy. Now, these conversions between mass and energy in most everyday cases are too small to detect. The amount of mass that would change, or the amount of energy that's created, is so small as you wouldn't be able to measure it or see it on a very easy basis. One example of this is an electron has a rest mass of about 0.5 mega electron volts. Now, the significance of this is that any reaction in which there's an appreciable loss of mass, there must then be that a certain amount of energy being created, and so that's a source of energy, or potential source of energy. And we're going to talk about two of those later on. Now, here's just some other brief applications that you can read through and take a look at. You can read through on your own. And we're going to talk much more about these two here, fission and fusion, in the next little section. This then leads us into what we call mass defect and binding energy. Now, what scientists found is that the mass of any given nucleus is actually less than the mass of all of the constituent nucleons added together. So it would be like taking 10 1 kilogram masses and putting them all together on the scale, and instead of having the total mass read 10 kilograms, it read 9 kilograms. Even though when you individually massed each individual object, each one had a mass of 1 kilogram, but when you put them all on the scale together, the mass was only 9. And this is essentially what scientists saw. And this was explained through the idea of mass defect. And the mass defect represents the energy that was released when that nucleus was formed. And so all those constituent particles came together. And again, just like anything in nature, things naturally want to be in their lowest, most stable energy state. And this is what happens when a nucleus is formed. And so the constituents come together, some energy is released so that that nucleus is in a lower energy state. That energy came from the mass of the constituents. And so now the total mass of the nucleus is less than all of that mass that was together. And that energy that gets released is what we call the binding energy. And so the mass defect is the difference between the mass of the constituents and the mass of the nucleus, and the binding energy is the energy that's released. And if we compare the two, or if we use Einstein's E equals mc squared, when we plug the mass that's lost into that equation, we should get the binding energy. And if we look at it a different way, the binding energy then is also the amount of energy that we would have to put back into the nucleus in order to break it apart. And we'll look at a table here in a second that shows the binding energies of different nuclei, but in order for a nucleus to get broken apart completely, that binding energy would have to be added back into the nucleus to break it apart. And then it would break up into those specific nucleons that made it up. Now here we have a graph showing the binding energies for our different elements. And make sure you notice there on the y-axis that what this graph actually is the average binding energy per nucleon. Okay? So it's not the total binding energy, it's the binding energy per nucleon. And so it's whatever the total binding energy is of that nucleus divided by the atomic mass, or the number of nucleons in that nucleus. And then down here at the bottom we have the actual number of nucleons, or the atomic mass of that particular nucleus. And so down here we have H1, and remember our H1, 1 and 1, because all it has is a single proton. Well, if you only have one nucleon, hopefully it's obvious that there shouldn't need to be any binding energy because there's nothing being bound. And so it has a binding energy of 0. From there we gradually go up through deuterium, tritium, our helium nuclei, and then we come back down to lithium, and we gradually build here until we get a maximum binding energy at the atom of iron. So iron has the highest binding energy per nucleon of any other element. And then we come down over here, and on the far right we have our plutonium, and we have our uranium, and you can see here it shows the different isotopes of each as well. And so the binding energy for uranium-238 is slightly lower than the binding energy for uranium-235. We have some other isotopes here as well. And basically this graph is affected as such in part because of the diameter of the nucleus. And so here, as we get larger and larger and larger, it takes more and more energy to break that nucleus apart. But once you get to iron, as you go past iron, the nucleus starts to get so large that it's becoming less stable, and it's taking less energy to break off each of those individual nucleons. So you can see how these two ideas, mass defect and binding energy, are really two sides of the same idea. if the mass of the nucleus were exactly the same as the mass of the constituent particles, that would mean that there would be no energy involved in putting it together, and no energy would be needed to break it apart, and so nothing would hold together. It wouldn't be stable. And again, this all kind of ties together. So the only way for a nucleus to be stable is if it actually does have a lower mass, and so that's part of why it's actually stable.